today me and my group will be doing our STEM model project.
So we're gonna make a barrier, which is the Anko barrier.
Guys, I forget to tell you one important thing that is very important in this project, which is the problem does need to be solved. And I'm so dumb that I forget to say it in the video, but I need to make it clear, okay? Based on second law of motion, the object will accelerate to the net force, and when the object's driving, when it stays still, that's another story. But when it moves, that's when you know that it is greater than friction. And it accelerates right down the bridge, and you don't want it to strike on the new bridge support, and people inside of the car will be injured. You know what I mean? So we created this barrier that will help reduce. Based on third law, there's going to be a reaction to it, action and reaction, you know. So the reaction will be the object bouncing off with the same force that it hits the barrier. So if it hits, like, it came really fast and it hit the barrier and then it bounced off really hard, people inside could be injured. So we created this barrier that could reduce the damage from the reaction based on like the material, the metal, and also the shape that is created from this barrier and all that. It helps. So we just want to try it out and see if it helps in this project. So yeah, that's what we need to solve, and I forget to say it, so yeah. Okay, so first we need to measure the mass of the car. So we did it, and it's 40 grams. What we need to do is this is our ramp, and we need to use it and then see how far it goes without the barrier. And then when we put the barrier on, we will see that it reduces the force that it hits. If that makes sense. Yeah, so let's start.
I will be dropping the car from the ramp and see how far it goes.
And I will measure it. Yeah,
And also the time.
and the timer.
I am here taking the video.
Yeah.
Okay.
Ready?
So what we'll be doing is writing it down. We're gonna do the exact same thing without the barrier, but with the barrier. So we stick barrier. So basically, the barrier it has like the W shape right here, and the real one, it will be made of metal, and that will reduce the impact, the force that the car hits the barrier. So our expected results will be the car bouncing back from the barrier, since it's third law. But then this barrier reduces the force, meaning that it will bounce lesser than when it comes, if that makes sense.
Yeah. Okay.
So I'll be putting it down because Bella is on. 3, 2, 1. This is the second trial, guys. 3, 2, 1. This is the third trial.
That when you say a nice one? Okay, good.
Okay, fourth trial.
So this time we're gonna do the same thing, but with more force, which means more the top of the ramp.
So the expected results will be the reaction should be less. No, should be more. It will go back from the barrier. Yeah. Second trial.
your trial. Four.
Round number 4.
Yeah. One, go.
So now we're gonna put more mass to it so that there will be more friction. Our expected result is that it bounced back from the barrier just a little bit, and it takes more time. Okay, so okay, guys, so we got a calculator, and I'm gonna calculate everything else that we need to. So what we're going to calculate here is the force, which is in Newton, and the formula is F equals ma. So you can see. So the first one that we're going to calculate is the one with steep and a barrier, the normal steep, not steeper. Okay. The mass is 40 grams. Okay. And we converted it to kg so that it will match the newtons. So it's going to be 0.04 kg. Now we have to find the acceleration, right? We got the mass now, we have to find the acceleration. Now the acceleration equals velocity final minus velocity initial divided by time. Of course, velocity initial will be 0, so we don't need that. Velocity final will be equals to 0.1 for the information that we got here. This one that we're using, 0.1. So we divide it by time that it takes, which is 2.9 seconds. And this one is meters per second. Now the acceleration will be equal to, calculator, 0.1 divided by 2.9 equals 0.03. Okay, meters per second square. But that's not it. We still need to find the force, right? So F will be ma. And we got the m, which is 0.04. 0.04. And divided by a, which we just got, which is 0.03. The answer will be 0.04 times 0.03. Answer is 0.0012 newtons. Alright?
These are the criteria that we have. The post that holds the W-shaped metals absorb the impact from behind the strip. The reaction then will make it lesser. The W shape of the barrier can only bend one way since it's designed that way, and it's hard to bend the other way, meaning that if the car hits it, it won't bend like many directions, and people inside will be safer. Then the constraints that we have is that it's not made for highways because you can't use it for extremely hard actions since the metal that people use are different, and some people tend to use like low quality metals, and that really will be extremely dangerous. So to just cut that off, don't use it in highways because people tend to drive faster there.
According to Nadi's calculations, the more steep the ramp is, the more impacts or force it has on the car, which means more accidents, and we don't want that. So to fix this problem, we'll have to make the ramp less steep and add the barrier to it, so that the car will have less impact, and it will be safe for everyone.
Okay guys, so this is the work. Thank you.